Okay, problem 12. This is a fairly long problem exercising the connection between thermodynamics and kinetics. Let me go back up to the top here and we'll look at the problem as it's actually stated. Here we are. So problem 12 here says that some measurements have been made on some chemical reaction for both the forward and the reverse rate constant, so both a K1 and a K minus 1. And that's been done at two different temperatures, at 300 K and at 330 K. At 300 K, we get K1 is a tenth of seconds to the minus 1, and K minus 1 is 100 seconds to the minus 1. At 330 K, the higher temperature, K1 is 10 times faster, 1 second to the minus 1, and K minus 1 is 2 times faster, 200 seconds to the minus 1. And then it asks several things. First, it asks find the equilibrium constant for the reaction at 300 K and also at 330 K. So find equilibrium constants. That's using the principle of detailed balance, right? The connection between thermodynamics and kinetics. And then it asks to find the enthalpy and entropy of reaction using those equilibrium constants, right? If we know how the equilibrium constant changes with temperature, we can find delta H and delta SR. That's going back to the thermodynamics section, but that's fine. And then find the Arrhenius parameters, so the energies of activation and the pre-exponential factors for both the forward and the reverse directions. And then finally, from all those results, draw a reaction energy diagram for this system. All right, so here we are over here now. And let me go back down to the actual answers so I can use the calculations that I have there to save some time. Here's the problem again, forward and reverse. Notice that because of the units on these rate constants, we can tell, even though it never gives what the reaction is, we can tell that it's a first order reaction in both the forward direction and in the reverse direction. So we know a little bit more about the reaction than is immediately apparent. First part, let's find the equilibrium constants. Actually, A here is find equilibrium constants at 300 and 330. Here we're using the fact that the equilibrium constant is equal to K1 over K minus 1, so these are pretty easy calculations. At 300, that's 0.1 over 100, which is 1.0 times 10 to the minus 3, and notice unitless, of course, because both K's have units of seconds to the minus 1. And then at 330 K, we have the same relationship, but now with different values for K and K minus K1 and K minus 1, so we have 1.0 over 200 seconds to the minus 1, and that's 5.0 times 10 to the minus 3. And that's at 330. So the equilibrium constant has gone up with temperature. It hasn't gone up by a huge amount, gone up by a factor of 5. That's a pretty good jump. Over the course of 30 degrees Kelvin, using the rule of thumb that we talked about earlier, remember that if you have a typical value for the delta H of reaction in this case of around 50 kilojoules per mole, then you would expect a doubling for every 10 degrees that you rise. You can see that we've gone up by three jumps of 10 degrees, and it hasn't doubled every time. That would be a factor of 8. Instead of it's only gone up by a factor of 5. So two things we can notice right away. One is the equilibrium constant went up, which means that delta HR has to be positive, right? It has to be an endothermic reaction. And second, that it didn't go up enough for delta HR to be 50 kilojoules per mole, so it's probably a little less than 50 kilojoules per mole. And so we already have, just qualitatively looking at these numbers, we already have at least a rough idea what to expect when we do the next part of the calculation. All right, that was part A. Let's do part B now. That's to calculate delta H R and delta SR. For delta H, we use the Van 't Hoff relationship, right? We use the fact that log K at T2 over K at T1 is equal to minus delta H of reaction over R times 1 over T2 minus 1 over T1. And so delta H of reaction is equal to minus R times the log of the two Ks, the two equilibrium constants, divided by 1 over T2 minus 1 over T1. Plugging numbers in, that gives delta HR is equal to minus 8.314. Log of K2 is 5 times 10 to the minus 3. K1 is 1 times 10 to the minus 3. So that's log of 5 for that ratio, divided by 1 over 330 minus 1 over 300. And if we plug the numbers into that, let's see what answer we get. We get 44 here, 44.16 kilojoules per mole. All right, notice it's positive, and it's a little less than 50 kilojoules. So both of the things we sort of qualitatively noted above turn out to be right. We now want delta S of reaction, and that is equal to, well, we get that in the following way. You can remember the formula, that's one way, but I never remember the formula, so let me derive it here. We know that delta G of reaction is equal to delta H of reaction minus T delta S of reaction at any one temperature. So let's pick T equals 300. And therefore, solving for delta S of reaction is equal to delta H of reaction minus delta G of reaction divided by T. And furthermore, we know that delta G of reaction is minus RT logarithm of the equilibrium constant at whatever temperature we're considering. And so that becomes delta H of reaction over T plus R log of the equilibrium constant. And this is going to be at 300, this is going to be at 300. Now all we have to do is plug numbers in. We have 44,160 for delta H in joules divided by 300K plus 8.314 log of 1 times 10 to the minus 3, right, for the equilibrium constant at 300. And plugging the numbers into that and going over here, that becomes 89.77 joules per degree Kelvin per mole. Okay, so now we're done with both A and B. The next part, we want all the Arrhenius parameters. So this is part C now. We want the energy of activation in the forward direction. We want the pre-exponential factor in the forward direction, and the same things for the reverse direction. We're going to use the Arrhenius relationship for this, but the Arrhenius relationship is essentially identical to the Van 't Hoff relationship up here. We're going to have that logarithm of K1 at temperature T1. Well, let me not even say whether it's forward or reverse. So for the forward direction, it's K at temperature T2 over K at temperature T1 is equal to minus EA over R times 1 over T2 minus 1 over T1. And notice, I kind of said this before, but let me point it out a little more clearly now. That's exactly the same equation as we just used for the Van 't Hoff, except that we used equilibrium constants, and instead of energy of activation, we had delta H of reaction. So the Arrhenius relationship and the Van 't Hoff relationship are really the same thing, except for changing the names on the variables involved. All right, so going back to our calculation here, that means that EA is equal to minus R times the log of the two rate constants at different temperatures divided by 1 over T2 minus 1 over T1. And that is equal to minus 8.314. Now for the forward direction, so we want forward rate constants here, times log of the two rate constants at the two different temperatures. So the forward rate constant is K1 at 330, and this is going to be K1 at 300. So K1 at 330 was 1, this was 0.1, and so we're going to have log of 10 here, divided by 1 over 330 minus 1 over 300. And that, if you do the calculations, gives us 63.17 for the activation energy for the forward direction over here. Kilojoules per mole. Okay. Now we want to get the pre-exponential factor in the forward direction. Remember, that's just equal to the K in the forward direction. In this case, let's choose 300 as our temperature. E to the minus EA over RT, which is just equal to 0.1, divided by E to the minus 63,170 over RT is at 300K, and so that's 2494, and if you plug the do the arithmetic on that, you get 1.0 times 10 to the 10. And now what about the units? Well, these units for A have to match the units for K. That's seconds to the minus 1, so 1.0 times 10 to the 10 seconds to the minus 1. And so now we have A for the forward direction. Now we just have to go through this same process for the reverse direction. So for the reverse direction, we have minus R log of K minus 1 now, the reverse rate constant at T2 over K at T1 over 1 over T2 minus 1 over T1, and that is equal to minus 8.314 log of K at T2 in the minus direction is 200, K at T1 in the minus direction is 100, so that's log of 2, divided by 1 over 330 minus 1 over 300, and that is, coming back over here to see the calculation, 19.02 kilojoules per mole. And so that's the EA for the reverse direction. And finally, the pre-exponential factor for the reverse direction is going to be K minus 1 now, the reverse, let's say at 300, over E to the minus EA in the reverse direction over RT. And that is 100 seconds to the minus 1, again, E to the minus 19,020 over 2494, and that is equal to 2.05 times 10 to the 5th seconds to the minus 1. All right, so now we have all four of those numbers. The last part of the problem is to construct a reaction energy diagram like this, so let's do that now. We now have the numbers that sort of say what the shape of this diagram should be. That's why we're not doing it till the end, right? We need some more information before we can write this thing down. So, in a reaction energy diagram, we have a reaction coordinate along this axis. We have reactants over here. We have products over here. We have a transition state in between. We have energy on this axis. We have a transition state in between. And we know the size of the barriers. We know the energy difference between reactants and transition state on both sides. We know that going forward, the activation barrier is 63 kilojoules per mole. So let's draw a picture like this. No, let's draw it like this. Let's suppose that we say that the reactants are at zero energy. We set our zero of energy. That means this should be at 63 kilojoules per mole, right? That's the barrier. So this distance has to be 63 kilojoules. And we know that the reaction barrier on the other side is only 19 kilojoules, only about a third as big, in fact less than a third as big as on this side. So this side's not going to come down as far, right? If this is about a third of that distance, then it's only coming down this far. And here's the products over here. And so the activation barrier going back the other way is only about 19 kilojoules. So going back that way, it's smaller. And let's see what else. We've labeled the transition state. We've labeled reactants and products. I think that's everything that the problem asks for, so I think we're done. We'll stop there and we'll do number 13 next time.